Hola amigos y bienvenidos al laboratorio de videos de inteligente. That made no sense probably, but what I meant to say was greetings gentlemen and welcome to the Smart Video Lab. So we're going to be talking right now about exponential functions. So this is off the review that I gave you in class. Now, nice thing about exponential functions is unlike linear functions, there's not a boat ton of forms to remember. There's really only one form to remember. And that is this, the general form, y equals a times b raised to the power of x, where a is the starting value and b is the common ratio. Sorry, it took me a while to say that. A is the starting value and b is the common ratio. So by common ratio, I mean b could be either a growth factor in cases of exponential growth, or it could be a decay factor in cases of exponential decay. So let's look at a general example just to get our brains going on exponential functions. The population of bacteria starts with 50 bacteria and doubles every hour. Write a function rule that represents the number of bacteria in after any number of hours x. So our form is y equals a times b to the x. But it says after any number of hours n. So instead of y, I'm going to use n. Now a is the starting value, so in this specific case, a is 50, the amount that we start with. And the growth factor, it is doubling every hour. So that means a growth factor of 2 raised to the power of x. So b is 2. So that's our equation right there. N equals 50 times 2 to the x. Exponential growth. Let's look at another couple examples. And specifically, we're looking at exponential growth and percent growth. So when you're given a growth percentage instead of a growth factor. So again, the equation is still y equals a times b to the x, where a is the starting value. But with growth, b has to be bigger than 1. So whenever b is bigger than 1, it's exponential growth. A student invests $500 into a college fund with an annual interest rate of 3.5%. How much money will he have in 5 years when he goes to college? So again, we start with a times b to the x. Now, it's clear that the a value is 500, the starting value. But in this case, the b value is a bit more complicated to figure out. So the b value in cases of percent growth is actually 1 plus r, where r is the rate as a decimal. So in this case, the interest rate is 3.5%, which as a decimal is 0.035. So b is going to be 1 plus 0.035, which is 1.035. So all that was to figure out the b value is 1.035 raised to the power of x. So that's the equation that represents the situation. Now if we want to know how much money will he have when he goes to college in 5 years, y represents the amount of money, so y is going to be equal to 500 times 1.035 raised to the fifth power, because it's 5 years that we're concerned with. And let's see what that comes out to be if I compute it in my calculator. So pulling out my handy calculator, 500 times 1.035 raised to the fifth power, that comes out as $593, and I'm rounding here 84 cents. So that's definitely not going to get you through college. You might want to invest a little bit sooner, or invest a little bit more money, or find a better interest rate. All right, example 2 says the population of Townsville is currently 400 people. If the population grows by 5% every year, in what year can they expect to grow to a population of 50,000? So let's make an equation to model the situation. Again, it's easy to see the starting value is 400 because they currently have 400 people. Now the rate is going to be 1.05. Sorry, the rate is 0.05. The b value, the common ratio, is 1.05. And how do I know that? because b equals 1 plus the rate. And in this case, the rate is 0.05. So that's 1 plus 0.05, which is 1.05. So it's 400 times 1.05 raised to the power of x. Now we want to know in what year can they expect to grow to a population of 50,000. Well, in the equation I just wrote, y represents the population after a certain number of years, x. So x represents number of years after the current time. So if I want to know when the population is 50,000, 50,000 goes in for y. And I have this equation that I now need to solve for x. So until you get to a higher level math class, you don't know how to solve this algebraically, but there's two ways we looked at in class. One was guess and check, the other was graphing. So if you like to use guess and check, go ahead and do that. I'm going to show you guys the graphing. So if I was going to graph this, I would graph f1 of x in the TI Inspire equals 50,000, and f2 of x equals 400 times 1.05 to the x. So I've actually already done that, and this is what it looked like. First, I entered in my f2 and my f1. It doesn't matter which one goes where, and I didn't see anything. So I had to go in and change my window settings. I changed the x-min to 0, x-max to 150, just to give myself a good range of the number of years that it might take that population to grow up to 50,000. Y-min was 0 because there's no negative population. That doesn't make sense. And then Y-max I made bigger than 50,000, so 55,000. And then I pressed OK. Now, once I graphed it, both lines, I was able to see it. And I said, yay, because that looks wonderful. And then I did menu, analyze graph, intersection. So menu, analyze graph, intersection. And then I set my lower bound and my upper bound, and it gave me this value here, this point, which 5e plus 4 means 5 with 4 zeros. So that's 50,000. So it's 99 comma 50,000, which means after 99 years, the population of that town is now at 50,000. So 99 years. Are we done? X equals 99. That's it? No, because it asks in what year. So what is 99 years after the current time of 2013? Well, 2013 plus 99, well, that's going to be 12 carry the 1, 11 carry the 1. That's the year 2112. So in 2112, that town can expect to have 50,000 people. And it might have been faster to do it by guess and check. It depends on the person, so I'll let you decide. Now let's look at an example of exponential decay as opposed to growth. Same form, y equals a times b to the x, where a is the starting value, but in exponential decay, b has to be less than 1. Notice in the last two examples of growth, b was bigger than 1. Not much bigger, but 1.035 and 1.05 are bigger than 1. Now exponential decay, specifically percent decay, b has to be less than 1. So a young man bought a truck for $6,000 and its value depreciates at a rate of 12% each year. Want to make a table for the value of the truck over 5 years, then write an equation that represents the value of the truck y based on the number of years after purchase x. So to fill in the table, you could either write the equation and use it to fill in the table, or use the now next rule to fill in the table. I'm going to use the now next rule. So I know that the next value in the table is going to be equal to the now value times, and this is where it gets a bit tricky, is it times 0.12? No, because that represents how much it loses. So if it loses 12%, it maintains 88% of its value. So I have to multiply by 0.88 each time. So next equals now times 0.88, starting at 6,000. So 0 years after purchase, the value of the truck is 6,000, and I'm just going to keep multiplying by 0.88 to fill in the table, and I'll pause the video and fill that in. So when you fill in the table, that's what it looks like. After 1 year, it's $5,280. This is value in dollars. After 2 years, $4,646.40. After 3 years, $4,088.83, and so on, going down to $3,166.39 after 5 years. Now the next question is, what is the value of the truck after 2 years? But I didn't answer the first part yet. We have to write the equation, duh. So it's y equals starting value 6,000 times, we know b has to be less than 1. So instead of 1 plus r, it's 1 minus r, where r is the percent written as a decimal. So b is 1 minus 0.12, which is 0.88, which we already alluded to. So it's going to be 6,000 times 0.88 raised to the power of x. That represents the value of the truck based on any number of years. I'm using that equation to figure out the value of the truck after 12 years. I just substitute 12 in for x, and you get $1,294.03 as indicated here. So I can use all this information, the table, and then this value to create a graph. The graph looks like this. X-axis, number of years, going by a scale of 1s all the way up to 12. Y-axis, value in dollars, went by every 2 blocks is 1,000. And this is what my graph looked like, just plotting the points from the table on the graph. You can see it's a nice exponential decay curve. So I hope you guys have enjoyed the exponential functions review. Hopefully you learned a lot from it. Love you. Have a good night or day.